Okay, very good. So the last speaker has come to visit us all the way from Munich and maybe to some extent Harvard. And he's going to tell us about PEPS with local gauge symmetry, studying lattice gauge theories with tensor networks in dimension higher than 2. So, Zohar.
Thank you. So I'd like to thank the organizers for giving me the opportunity to tell you about it, and I would like to thank the first speaker of this session for giving me the opportunity to skip some slides. I will tell you about what we've been doing at MPQ for possibly studying lattice gauge theories in more than one space dimension with tensor networks, in particular with PEPS. So, just to put us in the right context, we know that gauge theories are interesting in the context of high-energy physics as the theories that give us the standard description of the standard model's description of interactions and forces. But as we know, they also appear quite a lot in the context of condensed matter physics, which is one of the reasons people from condensed matter started to look at these things too. Why do we care about doing them with tensor networks? The local symmetry gives rise to many constraints, which usually looks bad, but this is actually something that we are going to exploit. They involve a lot of non-perturbative physics, and this gives rise, for example, to the confinement of quarks and the hadronic spectrum, to some exotic phases of QCD. There's a lot of interesting physics, but as we know, it's hard to look at this experimentally because the forces are too strong. It's hard to treat it analytically because we're talking about non-perturbative physics. And lattice gauge theory is a great thing that allows us to perform some lattice regularization in a gauge invariant way, but it can also have some problems. So in conventional lattice gauge theory techniques, one usually discretizes both space and time and performs Monte Carlo calculations on a Wick-rotated Euclidean lattice. And this has been extremely successful for many, many applications, such as the hadronic spectrum, but it has some problems which are the things that we are aiming at addressing. First of all, real-time evolution is something that is not available when you work in a Euclidean space-time, at least not directly. And of course, the sign problem that has been discussed before that appears in some scenarios with fermions. So new approaches that people in the quantum information community have been working on, and you will hear about it quite a lot in this workshop, are quantum simulation and computation, as well as tensor networks, which I'm going to talk about today. So I actually don't have to say a lot about tensor networks, thanks to the first talk of this session. So it's some particular construction of states, mostly on a lattice, but not necessarily, that allows you to describe or to solve, hopefully, many-body systems based on the constructions of tensors that depend on very few parameters. It's a very simple description, but they can describe and approximate physically relevant states of many-body systems very well, as we heard. Why should they be relevant for lattice gauge theories, at least for the two problems that we discussed? First of all, we are working in a quantum Hilbert space. We use the language of states, of time evolution of Hamiltonians. States, when they evolve in time, they evolve in real time. We don't have all the problems that come with the Euclidean space-time. So if there are some time evolution problems, they will be played on some other playground. And also the sign problem. In many cases, so here fermions are fermions. We don't have to use all these Grassmannian representations and we don't work in this Euclidean formulation where the sign problem arises. So once again, we have hope to go around it. So in the last few years, there have been quite a lot of works on tensor networks for lattice gauge theories, and I wanted to mention all the works and all the people, but it's become a bit impossible. So I think I could speak for 30 minutes about how I randomized the names that appear on this slide, yet I apologize if I forgot someone, but there have been quite a lot of works on the topic since approximately 2014. Okay, so we are talking about lattice gauge theory in the Hamiltonian formulation in a Hilbert space. What are we dealing with? First of all, we are dealing only with a space lattice. Time we take to be a real and continuous coordinate. The matter particles reside on the links of the lattice, while the gauge field, the matter particles reside on the vertices of the lattice, while the gauge fields are on the links. It's a Hamiltonian picture, so we have a Hilbert space, and it's very natural for describing constraints. The basic ingredient here is the gauge transformations. These are transformations that act on both the matter and the gauge degrees of freedom, on both the vertices and the links. They are local, which means that we can choose a unique transformation that depends on a particular group element of what we call the gauge group at each site that can be chosen separately, and the states have to be defined under action of... is there some light here, or? No light? Okay. This one? The stick, okay. Perfect. So the transformation is local, as we said. You can choose some gauge group element at each site, and then you have to act with some transformation that is parameterized by it and acts on the links around this vertex and the vertex itself. The states have to be invariant under each such transformation locally. We basically have some gauge group G, and we can label, if we want, the states on the links by elements of this group, and we define some group operations, some unitary operators acting on our Hilbert space that represent group multiplication. Out of them, we can construct these gauge transformations, but these are all technical details. The important thing is that our states are invariant under these gauge transformations at every site. Perfect, thank you. And if the group is compact, these transformations will be generated by something, by some generators. They will all commute with the Hamiltonian. They will all annihilate the state. And this is basically what we can recognize physically as the Gauss law. Some lattice divergence of the generators of the lattice electric fields on the links must be equal to the charge of the matter at the vertex. Which sorts of theories can we have? Let's go through the process of minimal coupling that we all know very well, but from the lattice point of view. So we can consider some simple Hamiltonian with fermions that hop from one vertex, from one site to the next. And this is, of course, invariant under some global transformations. This gives rise to the conservation of total number of fermions. And if I try to make this transformation local, I will see that it's not invariant anymore, just because of this kinetic term, just like the derivative term in the continuum. So what we do is to introduce some new object, some connection, a unitary operator that is attached to the link with its own transformation rule. Having to do with the parameters. In this case, we're talking about U1 here, the group parameters of the two vertices at the edges, and we get something which is invariant. This is minimal coupling on the lattice. We couple our gauge field, we couple our matter to a gauge field. So as we said, the fermions are located on the vertices. These connectors are on the links, and in the U1 case, well, in any case, but it's very simple to see it for U1, this U operator is simply something that is the lattice version or some coarse graining of the Wilson line along this link. So it can be seen as the exponential of a compact vector potential that will be conjugate to some integer quantity to some angular momentum, which is nothing but the flux of the electric field going through a face of the cube. And then we have some integer electric field, and this U operator is something that raises it. One can add dynamics. So in this case, these link interactions simply mean that you move a fermion from one vertex to the next while changing the value of the electric field in the middle. You can add a suitable kinetic energy term, angular momentum squared, which will just be the electric energy if you take the continuum limit. And you can write some interaction of the gauge field with itself, what we call the plaquette interaction, that in a continuum limit will become the non-interacting magnetic energy. So we have a symmetry, this gauge symmetry. This means that if it's continuous, it means that we have some conserved charge. The symmetry is local, so we have many conserved charges. In the continuum, we know that we have this Gauss law, the divergence of the electric field minus the charge. This is the thing that generates the symmetry transformations. Here on the lattice, we just have, in this U1 QED case, a divergence of the angular momenta on the links of the integer electric fields minus the charge on the vertex. This is something that commutes with the Hamiltonian. It's a conserved quantity. And this is valid for every x. Once again, local symmetry, many constraints. This gives some structure to the Hilbert space, because if it commutes with the Hamiltonian, all the states that are somehow physically relevant will be eigenstates of this operator with some eigenvalues, and these eigenvalues, which we identify as static charge configurations, split our Hilbert space into sectors that are not connected by dynamics, and then this actually forms some superselection rule. Okay. So we are going to construct some gauge invariant PEPS. PEPS, projected entangled pair states, are a particular tensor network construction, if you want a generalization of MPS to more dimensions, that allows to encode and to treat symmetries in a very natural way. It has by construction, as we saw, a bipartite entanglement area law, which makes it physically relevant. And it offers some nice features for studying phase diagrams and other properties of many-body systems. So how are we going to construct it? I'm going to construct my PEPS out of local ingredients that include both physical degrees of freedom that are going to be the degrees of freedom that I want to discuss in the model I study, as well as some auxiliary degrees of freedom that I'm going to use for connecting the sites. So I will start with some I will start with a single site. And here I will have this physical degree of freedom and the virtual one. I'm showing you how to construct it in two space dimensions. And this site I can create from some initial state, some local vacuum of all these degrees of freedom if you want, and I act on it with some operator that involves, let's say, creation operators or something that creates a state of these degrees of freedom. The next step will be to take a product of such objects on different sites. Still, the sites are not connected and they have no correlations. But then I want to obtain the physical state out of it. So I will introduce states that I will introduce on the links, on the bonds, maximally entangled states that entangle and connect, basically, the neighboring auxiliary degrees of freedom of neighboring links, and then I will just take my original state, which is not correlated, and project it onto these things. This, first of all, leaves me with a state that includes only the physical degrees of freedom, and besides that, introduce correlations and introduces some nice entanglement. And indeed, as you can see, entanglement area law is satisfied by construction. Okay, and then it's a very well-known procedure that has been used quite a lot in condensed matter to use this structure for demanding global symmetries, that the state will be invariant under some global symmetry group. This can be done if I do as follows. I construct my local tensor, my local site, in a way that if I act with some unitary operation that belongs to some transformation group on the physical degree of freedom, it will be equivalent to acting on the auxiliary degrees of freedom around it in some way that is parameterized by the same group element. This is one thing I have to demand. This is something I need to demand from the local tensors. Then I need to demand that the projectors, the maximally entangled state on the links I project on, will be invariant under such group transformations on the two edges. Let's see why this gives us symmetry. If I perform some global transformation on my PEPS, that is, I generate this Q as some local generator of my global symmetry, and this is just a product of unitaries. You see the same parameter everywhere, acting, these yellow circles, on the physical degrees of freedom everywhere. I act like this. Then, if this property is satisfied, if I parameterized my PEPS this way, I can just bring these symmetries down to the auxiliary level. If my projectors are invariant, I can just get rid of them, and eventually what I got is a state with a global symmetry. Now, what we can see is that this property is very, very similar to gauge invariance, to some gauge transformations. Why? When I showed you lattice gauge theory in Hilbert space in the beginning, we said that these gauge transformations act on some meter degree of freedom and the gauge fields around it and leaves the state invariant. Here what we have is something similar. Acting on the physical degree of freedom is equivalent to acting on the virtual ones, or if I just change sides here, I can say that acting on all the degrees of freedom leaves my local tensor invariant. But there is some difference, because here all our degrees of freedom are physical. And here, these things around on the legs that correspond to some electric fields in this analogy are not physical degrees of freedom. They are going to be traced out once I project all this state together. So when I construct a physical state, I lose this local symmetry. Yet, there is some way to extract it and make it physical. So this is what we call gauging of a PEPS, or if we want, minimally coupling a PEPS. I want to take the virtual symmetry and make it physical. I want to take a PEPS with a global symmetry and make it local. So I begin with a PEPS that I construct as before, something with a global invariance under this transformation group that I want to make eventually my gauge group. The first step is to introduce Hilbert spaces for the gauge field, because they need to reside somewhere. This will be quantum degrees of freedom. And I just add some gauge field singlet states, states that will be invariant under any transformation, to some legs that I set as outgoing. Still, it's just a product state of the gauge field and the rest. I don't have any local symmetry yet, any interaction. Then I'm going to entangle the auxiliary degrees of freedom on the legs with the gauge field Hilbert spaces that I introduced by what I call a gauging transformation, some unitary transformation that I will now introduce, which is basically some sort of minimal coupling, something that takes this non-interacting state with global symmetry and gives you something which is interacting with the local symmetry. So for U1, for example, what do? The auxiliary degrees of freedom that we have on each of the legs, let's say the generators of these rotation transformations, I call them ER and EU for right and up, some virtual electric fields. And these phi's are the physical vector potentials on the links. So I'm going to use this unitary transformation. It is a controlled operation that rotates the virtual fermions depending on the state of the physical gauge field. This creates an entanglement between them. And eventually, since I remind you that this e to the I phi is something that raises the electric field on the link, what this tells me is that I raise the physical electric field on the link by an amount which is completely equal to the virtual electric field I have there. So this is practically something that maps the virtual field to a physical one and gives me a state with a physical gauge invariance. So let's see what we did here. I started with this tensor, the building block of globally invariant PEPS, where if I transform the physical degree of freedom, it is equal to a transformation on the four legs around it. I performed this gauging transformation. I have new degrees of freedom, these electric fields. And now this satisfies these three properties out of the procedure I showed you in the previous slide. I act on all the physical degrees of freedom. This corresponds to acting on these auxiliary ones, which is just the result of taking these two auxiliary ones and lifting them to be physical. The other result of that is that acting on the other side, acting on these electric fields, will be equal to acting on the virtual degrees of freedom of the same leg. And when we make it non-abelian, it starts connecting to right and left transformations and all that. It works very well. So how does it work if I have a state that I constructed like this and I want to perform a local transformation? So you see, I act only here, around that vertex, on the fermions, on the matter, and on the electric fields around it. First of all, I have this property that allows me to take these three physical transformations and convert them to auxiliary ones acting here. Second, I can use these other two symmetry properties of the local tensor that I got through gauging and convert the last two physical transformations into auxiliary ones, and the bonds we haven't touched. They are as invariant as previously, so we got back the original state, and now we saw that the local symmetry became, that the global symmetry became local. What we want to use this for is to construct some states with which we can really study lattice gauge theory. So this will be states that describe fermionic matter coupled to some gauge fields. So what we do, we start from Gaussian fermionic PEPS with the global symmetry. Gaussian states, very simple non-interacting states, ground states of non-interacting Hamiltonians, of quadratic Hamiltonians. They are very easy to handle analytically. So we construct Gaussian fermionic PEPS that are globally invariant under the symmetry that we want. Then we make the symmetry local using this gauging procedure. This is similar to minimal coupling, but on the level of the state. I take a matter-only state which is free, I gauge it the way I showed you, and I obtain a state with a local symmetry with a dynamical gauge field with interactions, an interacting state, a non-trivial one that I parametrized when it was free. So then, if I originally parameterized some state with translation, rotation, and all that, this survive or get modified. But this global invariance becomes now local gauge symmetry. And then we looked at some toy models and studied their phase diagrams to see if we could have some physical phases that make sense, and I will skip this, but I will tell you that we saw some reasonable phases of confinement, deconfinement. The nice thing is how to use it for numerics, because MPS and DMRG have been extremely successful for lattice gauge theory, but these methods have a problem going beyond one space dimension. And with this method, we have a way to do it. And it works like this. I can define gauge field configuration states, which are states in which I just put some group element on each link, and I take a product of those. Then a general gauge invariant state will have this form. I integrate over all the possible gauge field configurations. I put the gauge field configuration and I multiply it by some matter state that is parameterized by this configuration. And this will actually be a state of matter coupled to some external gauge field configuration. For U1, we can do it just with these phases. Since these G states are orthogonal, we can perform some nice tricks. And in the gauge fermionic PEPS that we constructed, these psi of G are simply Gaussian fermionic states. So the complete state is not Gaussian. It has interactions, but we can expand it in terms of this, where the fermionic part of each element in the superposition is Gaussian. And this simplifies everything. So for example, if I take this U, this group element operator, and act on it on a gauge element state, on a group element state, which in this case is just a phase, it just becomes some function of the parameter, in this case e to the I phi. So I can take some operator whose expectation value I wish to calculate, for example, the Wilson loop. And what I eventually get is that I can calculate the expectation value using this classical function of these variables and some probability function, which is given by nothing but the norm of this Gaussian state. This is positive definite, it is real, it will never experience a sign problem, and this allows us to calculate these expectation values using the Gaussian formalism. It is very simple to calculate this norm because psi of phi, these states, are Gaussian. So then we can basically use this method to calculate any physically relevant expectation value that we want, such as the ones that appear in some Hamiltonian that we want to minimize. And we can use this method combined with Monte Carlo to variationally study lattice gauge theory Hamiltonians with Monte Carlo integration. And this we can do basically for other types of operators too. If we include fermions, it will involve the covariance matrix, which is very easy to compute for Gaussian states. And with other types of operators, like electric field operators, it's possible as well. And this allows you really to go beyond one space dimension and study lattice gauge theory Hamiltonians variationally, which is what we are working on at the moment. So just to show you some example, this is some simple phase diagram of a PEPS that we studied first analytically with an exact contraction, and then using these calculations. It doesn't show any interesting or new physics, it's just showing that computationally the method works before we go to the variational stages. And I wanted to say something about replacing the fermions by spins, but I think I don't have time for that. So I will just conclude and say that I hope I managed to show you today that PEPS could be generalized for the description of lattice states with a local gauge symmetry, that using the construction of PEPS, when you get a PEPS with some global symmetry, you have a well-defined procedure that allows you to make the symmetry local and add a dynamical gauge field, and that this gauged Gaussian fermionic PEPS may be used to study numerically lattice gauge theories in 2+1 dimensions and more. And that's it. Thank you very much.
Okay, very good. We have time for 2 quick questions.
So does this include the gauge self-interaction, the plaquette term? How do you handle this?
So it doesn't include any particular interaction because we construct a state. We don't construct a Hamiltonian. We construct a state that introduces that describes interactions between gauge field and matter. Then you use this state as some ansatz on which you apply a Hamiltonian that will include some interactions. But the particular type of interactions is not something we use for constructing the states. It's just a state that allows interactions and has the right symmetry. Then you match it with the Hamiltonian that gives rise to the interactions. We don't use the Hamiltonian to construct the state.
There was one more question.
So if I understood the gauging procedure correctly, you start with a PEPS made up of tensors that commute with your symmetry, and then you insert some additional 3 index tensors on the bonds.
Yes.
If I change the bond bases before gauging, do I get the same state after gauging? Or? So before inserting these 3 index tensors, I change my bond bases by introducing UU dagger on all the bonds. And now so is this procedure independent of the bases on the bonds? Or?
I think it wouldn't matter, yes.
But that would depend on what tensor you're inserting on the bonds, right? It should somehow commute with these UU dagger that you might introduce on the bonds before inserting the tensor.
Well, the thing that the bonds in any case carry some sort of a virtual field. And in my opinion, it doesn't matter which basis you use for that, because they are still used to transfer some information between the sites. So then you just have to gauge it, and I don't think that it will make a big difference.
Okay.
Okay, very good. So now it's coffee time. Let's meet here at 11:35. One quick announcement. I would like to ask Johanna and Christoph Karsch to come forward and upload their talks, and let's thank Erez for his talk.
Thanks a lot, Erez.